All right, welcome to Calculus 2 today. Today is the last day for new material on the upcoming exam 1. So remember, we have our first exam this Friday from 8 to 10 p.m. And it's going to be on lessons 1 through 14. I think today's 14. Yeah, it's going to be on all of those. We have a question. Yeah, what's up? What? Yeah, I am. I think I'm recording. Am I recording? Yeah, I see the little dot there. All right. Yeah, thank you. I forget all the time. I am recording, right? I'm not crazy. Okay. All right. Yes, we have our exam this Friday, and today is the last day for new material. On Wednesday, we're going to be doing some review in class. So you guys can bring any questions you have on any of the old exams I posted or the practice exam I posted. By the way, those exist. If you go to Canvas, the front page on the miscellaneous tab, you'll see links to some old exams you could try. And there's also, if you go to old homework / non-graded assignments, then you're going to see a practice exam on Canvas that you can take as well. So that will be, that's for you guys to work on. And then on Wednesday, we can talk about it. And then Friday during class time, we're going to essentially have office hours during that time. All right. So let's see. I think someone asked how many questions is it going to be? There's going to be 17 questions, and there were no, sorry. I always get this flipped around. There's going to be 15 questions, and there were 7 points each. But 15 times 7 is 105, meaning you have more points than 100 to get, but your score will be graded out of 100. Someone asked, is it all multiple choice? No, some of them are kind of like fill in the blank or like type in a number. But there's no free response. So there's nothing where you have to like show your work and submit it or anything like that. All right. Yeah, we could talk about more about that on Wednesday, but I really want to get to today's lesson because today's lesson ends up being, a lot of people tend to think this is pretty tricky. So I want to make sure we have enough time to go over this stuff. So lesson 14 is applications of integration, and this is going to be part 2. Okay, so last time in last class, we spent a lot of time computing the amount of work it took to move an object in a certain way or pump a certain amount of water or something like that. Now, what we're going to do today is we're going to compute something a little bit different. It's still going to be for physics. It's still going to be from physics, though. What we're going to compute is force due to fluid pressure. So let's say, for example, we have some water here, and there's a plate that's submerged underneath the water right here. So this plate is experiencing a force, right? It has all of this water or whatever fluid it is on it. So all the way above this plate, we have all of this water that's pushing down on it. So that's the force that it's experiencing due to pressure. And the bigger the area of the plate is, the more water it's under, meaning the more force it'll experience. And then also the deeper it is, the more water that'll be over it, the more force there will be for it to experience. Now this is a horizontal plate. So all the water is pounding directly on the top of it. But the thing is that the amount of force on this is going to be rho g HA, where H starts at 0 and goes down, so H is the depth. We're familiar with these two guys. These guys are constants, and then this is the area of the plate. All right, now the interesting thing is that the amount of force here on this horizontal plate is actually going to be the same amount of force as if this plate were flipped vertically instead. So we actually use the same equation for both the horizontal plate and the vertical plate, even though this one makes a little bit less sense because the water is not directly on top of this. The water is kind of like pushing on its side to side. But that's where the physics comes in. That's called Pascal's principle, where the same equation applies to both of these, no matter which way you orient the plate. So that's Pascal's principle. But we're not in physics. That's the only time I'm going to say that word or that name. So essentially, we just know that if it works on a horizontal plate, it also works on a vertical plate. Now, there is one complication with a vertical plate, though. Different parts of the vertical plate are at different depths. So for example, if we looked at the pressure on this little strip right here, the pressure on this would be different. It'd be more than the pressure we might have back up here. So the problem with vertical plates is that different parts of the plate are at different depths, meaning that they're experiencing different amounts of pressure. So this is where integration comes in. What we're going to do is we're going to divide our plates into these horizontal little strips that are all at the same depth right there. And then we're going to compute the pressure on each one of those and then add all of them together. Yeah, sorry about the pencil. I had 2 pens and they both died today. So I just have a pencil here. What do I mean by horizontal and vertical? So like this one's just flat underneath the water, kind of like this, whereas this one is up and down underneath the water. All right. So let's see here. Let's actually take a look at an example here. I'll try to write a little harder. All right, example 1. Find the force due to pressure on an upside down equilateral triangle plate with side length 2 meters. All right, so what's going on with this? So here's our water here, right? And then vertically, we have this triangle here. And this is an equilateral triangle. This is 2, this is 2, and this is 2. And we want to figure out the amount of force due to pressure on this entire plate. Now, the thing is that the pressure here near the top will be almost nothing because we're not very deep at all. And then the pressure down here will be quite large. But on the flip side, there's less of the triangle down here. Our little strips are going to be tinier the further down we go, but that's compensated by the fact that we're getting deeper and deeper. So we need to use an integral to figure out exactly how this is going to work here. All right, so let's look at our equation here. Remember, the force due to pressure is rho g h a. Remember, h is 0, and it increases as we go downwards right here. All right, rho and g are constants. H is just a variable that's going to be there by default. So essentially the thing we need to do every single time with this is compute what A is. And for A is the area of the rectangular strips. And we're always going to use rectangles. So sometimes people suggest like, oh, maybe we should use like a trapezoid because that will fit the triangle better. Well, we're always going to use rectangular strips. Reason being is that finding the area of a rectangle is very easy. So we're just going to stick with that. All right. Now let's see. The area of a rectangle is just the product of its side lengths, right? So what do you think I'm going to call the length right here? What do you think is a good name for this length right here? DH. That's right. We're going to use DH because H is our variable for how deep we're going here. Now, what we really need to figure out is this, which I'm going to call W of H right here. This is the width. And I say it's a function of H because obviously if we go less deep, it's going to be bigger. If we go deeper, it's going to be smaller. So our area is going to be the width and then times DH. So what these problems boil down to here is essentially figuring out what function our width is going to be. Okay, so we need to come up with what function we should use for our width right here. Now let's see here. Let's go to the top. So when we're at a depth of 0, what is the width of our rectangle going to be when we're at the top of the water here? It's going to be 2, right? Now let's see here. Actually, first of all, we need to figure out how far down this goes. It's not 2 because 2 is this diagonal distance. Does anyone know the height of an equilateral triangle with side lengths of 2? How deep is this going to go? Yeah, square root of 3. That's right. And we could figure that out. If you didn't know that, that's okay. We can figure it out because we divide this in half, right? So this is 1. That's this right here. So we would have 1 squared plus a squared is 2 squared. So we subtract that over. A squared is 3. So the height is going to be root 3. Okay, so then now let's get back to this. When we're down at the depth of root 3, when we're at the bottom of our triangle here, what's the width of our rectangle going to be there? 0, right? Because these things are getting smaller and smaller and smaller, thinner and thinner and thinner, until finally, when we get all the way down to the bottom, they're not going to be there anymore. So we have a width at root 3 being 0. Now, one thing we can observe here is that this length is decreasing linearly, right? We have these lines here, and they're getting closer and closer together. And they're doing so at a constant rate because these are lines. So what we can do is we can come up with a line equation for W, because its boundary is lines. So that means that how big it is going to be determined by the equation of a line. And the good thing is that we have 2 points on this line. So we can figure out our slope is going to be 0 minus 2. Oh my God. Divided by the square root of 3 minus 0. Like that. Is there no pressure at square root of 3 because of the 0? That's right. Yeah. So the pressure at this particular point is 0 because we don't have any area anymore. And also the pressure at the top is going to be 0 because we don't have any depth. So the slope of this line is going to be -2 over the square root 3. Oh yeah, I guess we have the ambient air pressure. We're not going to worry about that. We'll save that for physics. Anyways, we end up getting a slope of -2 over root 3, like this. Okay, now we also know that when we plug 0 in, we have an x value of 0, we get a y value of 2. So 2 is going to be our y-intercept, right? So W of h, our line, is going to be -2 over root 3. Oh my God. 2 over root 3 times h plus 2. So this is going to be our width equation right here. And if you ever are skeptical of this, you can always plug in the points that you know about just to check to see if it's right. So for example, if I plug in 0 here, I'm at a depth of 0. This will all be 0, and then I end up getting the 2 that I want. If I put in root 3 right here, I have root 3's canceling out, and then I have -2 plus 2 will be the 0 that I want. So this ends up working out. And it's the equation of a line, and we notice that we have these diagonal lines bounding our shape. All right, so now that we know our width, we can go ahead and stick that into here. And this part, by the way, figuring out what this function is, this is going to be most of the problems here. Kind of like the applications that we've done before, usually the integrals aren't going to be too hard. So the integral part isn't that bad. It's usually just figuring out what this is. So the force on one little slice is going to be rho g h, and then -2 over root 3h plus 2 dh. So that's the force on one little slice at a depth of 8 right here. Is W of h dh the area of the rectangle? Yes, it is. That's right. And we need it because in terms of h because of the dh, that is also correct. Yep, that's exactly what's going on here. All right, now as usual for any of these applications or any of the volumes or anything that we've done with integrals, when we get it for one little slice or chunk, if we throw them all together and we add them all up, that's going to turn into an integral. So the total force here is the integral of rho GH and then -2 over root 3h plus 2. And then, now let me ask you guys this. What are the bounds of the integral going to be? And remember our philosophy, the bounds are always going to be where the object is. What are the bounds for this integral going to be here? 0 to root 3, absolutely. There we go. Okay, now today what I'm going to do for most of these is I'm just going to skip doing the integral part, because if I were to rewrite this a little bit, it'd be rho g and then our integral, and then it'd be h times 2 minus 2 over root 3h. And if I were to FOIL this, I would get 2h minus 2 over root 3h squared, and then that would just be a polynomial integral right here. So I trust that you guys know how to do a polynomial integral. You essentially just do the power rule multiple times, and then you get your answer. So I'm gonna save this guy for another time, because I want to make sure that we actually get through setting up all these examples here. So I'm just going to leave it like this here. All right, so now I want you guys to give this a try. And don't worry, it won't be too bad. It'll actually be an even easier example than this was. I'm going to scoot this up a little bit. Okay, so for our first practice, I want you to find the force due to pressure on a rectangular plate with a width of 4 meters and a height of 2 meters, whose top is touching the surface. So the top, the flat top part of this rectangle is touching the surface of the water, and then it starts going underneath. Why don't you guys do that? And for all of these problems, I recommend drawing a picture, just the same as the applications that we had before. You really want to draw a picture for these guys. Yeah, fun. Yeah, thank you. Yeah, that's a lot better. What do we mean the top is touching the surface? It means the same thing that the top of this triangle was touching the surface. It means there's no water in between this and the top. Trying to position this so we can see everything. Since the width is constant, do we not do a function? Well, you would use a constant function. So it'd be pretty simple. Yeah, the rectangle is vertical, and all of these plates are going to be vertical here. And remember, it doesn't really matter that much because of Pascal's principle. It doesn't matter what the orientation is. So we're just going to do all of them as vertical. So if it's not on the surface, will we just change the bounds? Mostly, yeah. We'll see an example of that. Is DH still involved? Yeah, DH is still going to be involved. So remember, the DH is always the height of the rectangle, and then the width is what we change for each problem. All right, seems like we're getting some answers here. You're close, Kayla. The strips are always going to be horizontal because we want everything to be at the same depth, so they have the same pressure. Ooh, it looks like we have a schism between 16 rho G and 8 rho G. Yeah, that's right. Area is 4DH. You guys another minute or so, then we'll go over this. All right, let's take a look at this guy here. All right, so find the force due to pressure on a rectangular plate with a width of 4 meters and a height of 2 meters. All right, so here's our water. So we have a width of 4 meters, so that's what this is. And then a depth of 2 meters, like that. And the top is touching the surface of the water here. All right, now what we're gonna do is we're gonna do the same thing that we've done with every other problem. We're gonna divide this up into slices. So the force on one slice is gonna be rho G HA, where H is 0, and it increases downwards. So the area of this will be its height, which is going to be DH, times its width, which will be W. All right. So let's see here. Now, this time the width function will actually be a lot easier to determine. What's the width of all of these rectangles, no matter what depth they're at? It's going to be 4, right? Because even if I moved it up here, it's going to be 4. If I moved it down here, it's going to be 4. So our W functions is about as easy as it can be. It's going to be 4. Our width is always 4, no matter what our depth is. So we could arrange this in a more aesthetically pleasing order. And there we go. So that's the force on one slice of this. So now what we're going to do is we're going to throw everything into an integral. Okay, now let me ask you guys this. So this is the total force now. What are the bounds on this integral going to be here? Where is the object? 0 to 2, that's right. All right. And we'll actually do this one because you need to know the answer for this. So we're going to integrate h. So we're going to raise it to be an h squared, and then we divide it by 2. We have 2 rho g h squared from 0 to 2. And then we plug in 2 into here. 2 squared is 4 times the 2 we already have is 8. And then I plug 0 in here. Well, that's just going to be 0. So it looks like the 8 rho g's had it. This is going to be the force due to pressure on this plate. And just as a reminder, we don't need to know any particular densities for any fluids or anything like that. You don't need to know what number G is. We're just going to leave our answers just like this. All right, now I'm actually going to do things a little bit out of order. If you guys are following along in the notes, I'm actually going to go straight to the second practice problem to make sure that we have time to do it. And then I'm going to go to example 2. But you guys already have everything you need to know to do practice 2. All right, so suppose the triangle, well, I guess I should draw it like this. The triangle from problem 1 is pushed 3 meters under the water. But it's still going to maintain its orientation. So it's still going to look like this. Set up, but do not evaluate the integral to find the new force. Due to pressure. So just for reference, let me write down what the old one is. So the integral that we found earlier. Does someone have a question? All right. This is the ghost. The rho GH negative 2 over root 3h plus 2dh. So this was the old integral that we have. So now I want you guys to see how moving the triangle from here down to here will change things. And it should change things because you're deeper under the water, right? So you should experience a different amount of pressure. So something in this integral should be different, or maybe multiple things. And remember, you don't have to solve the integral. In fact, I think on Canvas, they don't. They just have a few different integrals to pick from. So the area is not changed, but the bounds do. Well, I'd be careful about your width function. That might need to be a bit different. Because your width function assumed it would be a width of 2 at the surface. Now we're at a width of 2, 3 below the surface. Yeah, that's the right idea. It might need to be translated. You guys do this in physics 1, this kind of stuff? Has anyone, you know? Oh, okay. Okay. Do the work calculations, okay. Yeah, they say it's physics with calculus, but they actually don't even use too much calculus. Yeah, they use derivatives when they're doing the kinematic stuff. And it's mostly it. They talk about the right-hand rule. Yeah, I only know the right-hand rule. All right, give you guys another minute or so. All right, let's do this guy here. All right, so we want a new integral here. Now let's write down the stuff that we know is going to be the same. The rho and g, those guys are just kind of hanging around. So we're going to have those again. H is always symbolizing the depth. So we know we're just going to have that by default in the formula. The only thing that might be different is our width function and our bounds. So remember the golden rule with the bounds always are saying where the object you're working with is. So what are the new bounds going to be for this integral? Yeah, they're going to be 3 to 3 plus the square root of 3, because we're shifting everything down by 3. Now you might think, okay, well, the width function is the same because it's going to be the same shape. But the problem is that this width function, if we recall what we did earlier, it gives a width of 2 at the surface and a width of 0 at root 3. But that's not really the case anymore. We want a width at 3 to be 2, and our width at 3 plus root 3 to be 0. Okay, so let's try to figure out what the line for this is. Well, the slope of this line will actually be the same. That part's unchanged because we have 0 minus 2 and then 3 plus root 3 minus 3. So the 3 shift didn't do anything here. So the slope is the same. So we know that our width is negative 2 over root 3h and then plus some number. Now we don't have the luxury of just having the y-intercept anymore because this is at 3 now, but we could just plug in one of these points to get that, to get what b is. So I'm going to put 2 into here, and I'm going to put 3 into here. And so let's see. If I add this over, I have 2 plus 2 square root of 3 is going to be my b right here. Because 3 over root 3 will simplify to a root 3 on top, and then I added it over, changing the sign. So this time my width function is negative 2 over square root of 3h plus 2, and then plus 2 root 3 as well. So that part is going to be a little bit different as well. So this and the bounds are different, but everything else remain the same. These are just inherent in the formula. All right, so now we know how to deal with situations where we shift something underneath the water. It's not too different from when something's at the surface of the water. Okay, now I want you guys to buckle up for the next example. This one is going to take probably a decent amount of time, so get ready for this. Try not to zone out. I know that sometimes this can be kind of difficult and long, but I really want you guys to focus on this next one. All right, so the next one I'm going to do is example 2 in the notes right here. This isn't an option in Canvas. Did they do h minus 3 maybe? Yeah, another way of writing this is negative 2 and then h minus 3. Like that. Oh, and then plus 2. Oops. There we go. All right. Let's move on to the next example. This one's really going to require us to think here. So find the force due to pressure on a circular plate of radius 1 meter, whose top is 2 meters below the surface. Okay, so as always for these, let's draw a picture. So let's see, here's our surface. Here's our circle. It's of radius 1. And then we're doing this at a depth of 2. Okay, so we want to find the force due to pressure on this. All right, so let's see. Let's take a slice of this circle right here. So we have this rectangular slice. Now, as always, the force on one of these slices is rho GHA. Oh, there we go. Thank you. To the left. Rho GH, and then A is going to be W of H DH. That's the same thing every single time right here. Now, as always, the tricky part is figuring out what our W of H needs to be. Now, the W of H should match the shape of the object. So in the previous problems, with the triangle problem, we use lines because the outer edge of our shape ended up being lines. But now the outer edge of our shape is a circle. So rather than using a line equation, we're actually going to be using a circle equation this time to get our W of H. Okay, so this is where the rubber meets the road. So pay attention to this. What I'm going to do is I'm going to make a coordinate axis. I'm going to draw a line straight through the middle of this and down. And as we all know, this is the H axis. This tells me how deep I am. And H, remember, it gets bigger, more positive as we go down this way. Now, I'm also going to have another axis. I'm going to have an axis going to the right and this way. What do you think a good name for this axis would be? Okay, yeah, W would actually be okay. What is this axis normally called? It's the x-axis, right? But it will have a relationship to W, though. So X is going to be our horizontal axis, and it gets positive going this way, right here. Okay, so what I want to do is in this coordinate system, with X being the horizontal and H being the vertical, but going downwards, I want to find the equation of this circle. That's my goal right now, because the equation of the circle will have to do with the width. All right, now let's see here. The equation of a circle is x minus h squared. Oh, oops, well, I better not use h. Let me use a. Plus h minus b squared is the radius squared. Okay, that's the equation of a general circle at center AB, radius r. Okay, well, we can fill in the radius part right now. The radius is 1. That's not an issue. Okay, now let's see here. Here's the center of the circle, right? It's right here on the h-axis. It's not to the left or right at all. So what is my A going to be here? What's A? A is going to be 0. Because remember, we're not left or right at all. We're right there in the middle. So we have x squared. Okay, now what is the h coordinate for our center? That one is going to be 3. Because we have to go down 2 to even get to the circle, and then it has a radius of 1. So we need to go 1 more to get to the middle. So the h coordinate of the circle is 3. Well, remember, h increases as we go downwards because it represents the depth. All right, so what we're going to do now, remember, our whole goal is to get the width, right? And we want it to be a function of h. Now, let's take a look here. X always represents the horizontal distance from the axis to the curve. So there's X. Now, what is the relationship between W and X? So W is equal to what with X's? It's 2X, right? Because we have X going this way, and then we would have the same distance going the other way because the circle is symmetric. So W is going to be 2 times whatever X is going to be. So now all that means I need to do is solve for X and then multiply by 2. Then I'll have my W. So I have X squared is 1 minus H minus 3 squared. All right, X is the square root 1 minus H minus 3 squared. And I'm picking the positive version because I'm doing lengths. And then I multiply everything by 2. So W is 2 times the square root of 1 minus H minus 3 squared. All right, there we go. So that's how we get W for this one. Can I explain the relation between X and W again? Yeah, that's kind of the crux of this. So remember, whenever we want to measure a horizontal distance from our axis to the curve, the appropriate name for that distance is X. That's what we've been doing ever since we learned about coordinate systems. X measures the horizontal coordinate system. All right, so then that means this distance right here is X, but I want the whole width here. That means I need to go X in this direction as well. So since I'm going X in 2 different directions here, I have 2 versions of this X. My total width is going to be both of those combined, or 2X. Yeah, what's up? Yes, the width changes depending on what H is, and hence we have this equation right here. So, and if you're ever uncomfortable with this, we could plug in some numbers and see if it works. So for example, at H equals 2, we should get 0, right? Because our box will kind of disappear. So if I plug 2 into here, I have 1 minus 2 minus 3 squared. That will all be 0. Right. How did the X minus A squared become X squared? It's because we're not to the left or right at all. We're right here, smack dab in the middle of our axis. So our X coordinate for that was 0, right? All right. Oh, did you have a question? Oh yeah, A is because we're not to the left or right at all. It's the X coordinate for our center. All right, now that we have this width right here, we're going to take it and put it into our thing up here. So the force on one slice is rho g h and then 2 square root of all this stuff, dh. And as always right here, once we get the force on one slice, then we're going to integrate the whole thing to get the total force. All right, so let's see. I'm going to put the 2 right there. Okay, so this is my integral right here. All right, now as always, we need to discuss the bounds. So I want you guys to figure this out. What bounds are we going to have for this integral? And remember, it's always where the thing is. 2 to 4, good. I'm glad you guys are getting this. This is great. So it's 2 to 4. That's where the circle is in terms of our coordinate system. Okay, now this one I actually will go through and integrate. And the reason is that there's actually 2 really useful integration techniques that I'm going to be using here that can really speed things up on the occasions you get to use them here. All right, what I'm going to do first is I'm going to do a U substitution. I'm going to do U is H minus 3. So du will be dH. All right, this is one of the rare application problems where we actually need to use our new techniques. Most of them were just power rule or whatever, but this time we need to use a little bit more than that. All right, so let's see here. If I do this, that means that U plus 3 will be H. So I have rho G2 u plus 3, because that's what my h is now. And then I have the square root of 1 minus u squared du. All right. Now let me ask you guys this. What are my new bounds going to be in terms of u right here? So if I plug my old lower bound into here, I have 2 minus 3 is -1. And then I plug my old upper bound into here, 4 minus 3 is 1. Well, in terms of u, we end up getting -1 to 1. Okay. Oops. Let's move this up here. Oh boy. All right. Okay, let's see here. So what I'm going to do now is I'm going to distribute this and make this into two different integrals. So I have the integral from -1 to 1 of rho g 2u square root of 1 minus u squared du. And then I have the integral from -1 to 1 of rho g 3 times 2 square root of 1 minus u squared du. And why I didn't write that as a 6, I will explain in a moment. Okay, now this is going to be really slick right here. Normally, we would need to do some u substitution and some trig sub to do this, and this would take a whole heck of a lot of work. But actually, for both of these integrals, there's something really nice we can do right away. Yeah, what's up? Oh, I mean, yeah, we could do that if we want. So if you want to, we could write rho and g outside of here if we want to. Yeah, that's no problem. Okay. So let's see here. Let's take a look at this function right here. 2u times the square root of 1 minus u squared. So this is kind of like the meat of the integral. Like he was saying, we can just move the constants out of here and not worry about them. This is what we're really focusing on. Okay. So I don't know how long it's been since you guys have been refreshed about this, but do you guys remember odd and even functions? Does that sound like something that you may have heard of before, at least? You've heard of those? Okay, so do you guys know what type of function this is? Is this odd, even, neither, maybe both? Which one is this? It's an odd function. That's right. Oh, what is even and odd? Let me remind you of that. For odd, f of negative x is negative f of x. That means that the odd spits out the negative. With even, f of negative x is f of x. In this case, it eats the negative. That's what's going on here. And in this case, if we plugged in a negative here, it wouldn't do anything to this because that's a square, but then it would just gain a negative here. So this is an odd function. Now I'm going to show you something really awesome. If you have the integral from negative a to a of an odd function, it's going to be 0. So if you integrate an odd function over a symmetric interval like -1 to 1, you're going to instantly get 0, no matter what type of odd function it is. And why is that? Well, odd functions have the property that their graph is reflected about the axis like this. So if they have anything positive over here, they're going to have the matching negative version on the other side. So as long as you take equally from both sides here, they're going to exactly cancel out. That means that this integral we have here is a big old 0. So there we go. We have managed to avoid having to integrate that directly. And that's something to kind of keep your eye out for. And that's something that may be helpful on a future homework, for example. So I would keep an eye out for that. Another trick that we're going to do to obviate doing trig sub right here is we're going to take a look at this function. Let's see here. So we actually saw something similar to this earlier on in the class. like just a few minutes ago, what kind of shape did this come from? Square root of a number minus a variable squared. It's not a triangle. It's a circle, right? So earlier we got this equation from a circle, right? And this one's pretty similar, honestly. This one's similar, except we just have it at, we just got rid of the -3 there. So what we're doing, so the square root of 1 minus u squared, if we were to graph that, it would just be the top half of a circle. And it's only the top half because when we did the plus or minus, we picked a side. So we picked the positive end, meaning it's only going to be the positive here. But what would we get if we doubled this? Well, if we doubled it, we would just get a copy of it down here, and we would get the whole circle, right? If we doubled this, we are doubling a half circle, meaning we get a full circle. Okay, so with that in mind, let's come back here. So what's the radius of this circle? Oh yeah, we have a question. Yeah, I guess I shouldn't have drawn this. That was a mistake. I was thinking it was a mistake as I drew this. So we're effectively doubling the half circle. So it's like we have two of these. So then we're just going to be able, you could kind of stick it there and make the whole circle. That's what's going on here. All right, now let's go back to this. What is the radius of the circle in this integral right here? It's 1, right? Now, what's the area of a circle of radius 1? Because remember, whenever we see this in an integral, this is talking about a circle. So what's the area of a circle of radius 1? It's going to be pi. So this rho g in 3, this is a constant. Like we said, we could take it out. So we have rho g3 times pi r squared. Because remember, the integral of this stuff is just measuring the area of a circle. Integrals measure area, and we have a circle right here. So we have rho g3 times pi 1 squared. So our answer to this entire problem is 3 pi rho g. And that's going to be it. So these are two extremely sneaky ways of doing integrals. Now, I wanted to offer the disclaimer. I did not expect anyone to like intuitively know how to do this. So don't worry about that. This isn't something like I expect you to kind of just magically come up with it on exam. But if you ever have definite integrals in the future, these are two things that you could take advantage of to avoid doing a bunch of work. Whenever you can use these, I really recommend that you do, because you can save yourself a bunch of work. But if you don't feel comfortable using these, that's totally fine. You could just go ahead and use u sub to do this one, because you could do u as the whole inside, and you could use trig sub to do this one if you wanted to. It would take longer than what I just did here, but you don't have to use this kind of slick stuff right here. All right, and then there's one more problem. I said I would put the one up that I skipped last time, so I'm going to put up the one I skipped last time, and then this one right here that I'm going to skip, example 3. I'll post those a little bit later here. All right, well, that's about it for our applications here, and that's about it for the chapter's material. So on Wednesday, we're going to be doing some review. So I will see you guys then.